Hello, my name is Faigl, and I am from the Czech Technical University in Prague, where I am heading the Computational Robotics Lab within the Artificial Intelligence Center. In this video, I would like to share our results on fast sequence rejection for multi-goal planning with Dubins vehicle. The study problem is motivated by data collection planning to visit a set of locations using an aerial vehicle. The problem is multi-goal planning, that is a robotic variant of the traveling salesman problem. In our case, we use a fixing vehicle for which feasible paths are curvature-constrained. Therefore, we employ Dubins vehicle model with constant forward velocity and minimal turning radius for planning optimal point-to-point curvature-constrained paths. For such a vehicle, this state is expressed as a position of the vehicle in a plane and its orientation as the heading angle theta. For a given vehicle headings at the locations, the optimal point-to-point path is Dubins path that can be found analytically using closed form expressions. However, the headings are not known in the Dubins DSP. Furthermore, the DTSP is sequence dependent, where the optimal path from one location to another location depends on the previously visited location. We can formally define the Dubins Traveling Salesman Problem as a problem to determine a shortest Dubins tour visiting the given set of n target locations. It consists of two optimization parts. The first is the sequencing part, which is the underlying TSP to find an optimal sequence as discrete combinatorial optimization problem. In addition to that, there is a continuous optimization problem to find the optimal headings at the locations. These optimization problems can be put into a single objective function to find the minimum Dubins tour over all possible sequences and heading angles, where the individual length represents Dubins path from one location to the subsequent location in the tour with the optimal headings. We can find several approaches to the DTSP in the literature. There are decoupled approaches that address the sequencing part independently on the optimization of the headings. For example, we can use the Euclidean TSP for finding the sequence. Then, for such a sequence, we can determine the headings using heuristic alternating algorithm or other more sophisticated optimization methods. The transformational methods transform the DTSP into a pure combinatorial problem using sampling of possible headings into finite discrete sets. So, from an instance of the DTSP, we create an instance of the generalized asymmetric TSP that can be solved optimally for the use discretization, or we can use a heuristic solver. Finally, there are direct methods that address both optimization parts together. For example, using evolutionary technique or online sampling of the headings, as we did in unsupervised learning-based approach. If we stay with a sequence of visits, we need to determine n heading angles, which is an n-variable optimization problem. We call this problem as the Dubins Turing problem, DTP, in our paper from ECMR 2017 to highlight that the Dubins Turing problem is a fundamental building block for solving routing problems with Dubins vehicle. There exist several approaches to the DTP, including tight lower bounds. However, in our case, we consider sampling of the heading angles similarly as in the transformation methods. So for a given sequence of locations, we sample the heading angles and create a discretization schema HK. Then the cost of Dubins tour defined by the sequence sigma is found as the assignment of the discrete heading angles that minimizes the sum of individual paths between the locations in the sequence. For k headings per each location, the cost of Dubins tour can be found in polynomial time using a graph search. The graph can be constructed for an instance of the DTP as follows. For each location in the sequence, we create k nodes representing the individual headings. Then we create k-squared connections between the consecutive locations. Because the Dubins tour in the DTSP is closed path, we have to ensure that the arrival heading at the initial location is the same as the leaving heading. Hence, we need to examine k options for the heading at the initial location. Thus, the optimal Dubins tour for the sequence sigma and given discretization can be found in nk cubed. Having a solution of the DTP, we can solve the DTSP as a finding the best sequence among all possible sequences that are assessed as a solution of the Dubins Turing problem. So, we need a generator of sequences and we need to assess candidate sequences to test which sequence is better. As a sequence generator, we consider the variable neighborhood search, the VNS, that is a meta-heuristic for solving combinatorial and global optimization problems. the VNS was introduced by Mladenovic and Hansen in 1997. The idea of the neighborhood is from modifying some incumbent solution using shake and local search procedures. Inside these procedures, operators are utilized that can alternate the sequence into a different sequence. The neighborhood represents all possible sequences that can be created by applying a particular operator. The VNS has been deployed in many combinatorial problems, and we employ an existing method for solution of the DTSP. So in our shake procedure that tries to escape from local minima, we use two operators, insert and exchange, that are visualized in the figure on the right. In local search, we use also two operators, pass insert and pass exchange. What is very important for the results presented in the paper is the observation that during generating sequences in the variable neighborhood search, for example in the shake insert operator, we can notice that the vast majority of the sequence remains untouched. So the white parts of the sequence are the same after inserting S2 between S3 and S7. The new sequences thus share a large portion of the subsequences which is exploited in the proposed fast sequence rejection. The idea of the proposed fast sequence rejection is based on quick estimation of the sequence quality. If we have a sequence sigma with the level round cost that is above the true cost of the currently best sequence sigma star, we can reject sigma because it cannot be better than sigma star. We propose to compute such level bound using the windowing schema of the open path. The open path allows to reduce the complexity of the graph search from nk cubed to nk squared. However, we further split the computation of the level bound to a sum of cost of short Dubins tours using the windowing schema. So for a window of the size 1, we compute the Dubins tour connecting two locations and these two locations and these two locations and so on. We can expect that with increasing size of the window, the level bound estimation would improve. However, it will be more computationally demanding. There is a trade-off because for window size significantly smaller than the number of heading samples, we can speed up the computation from nwk squared to nk squared. But we can also see that for long windows there is not a direct computational benefit to the true cost with the complexity nk cube. However, the benefit of the windowing schema is in splitting the computation using short subsequences for which we expect to reuse the solution in examination of the newly generated sequences using, for example, a hash map data structure. Let's examine the possible benefits of the windowing schema theoretically. We assume that solutions of the W-size subsequences can be stored and utilized in the assessment of a new sequence, for example, using a hash map data structure. We can pre-compute all Dubins paths between all n locations with k headings in n squared k squared. The true cost of Dubins tour for a sequence sigma with the discretization schema hk can be found in nk cube. Regarding the subsequences, the number of unique subsequences increase with the window size, but we do not need to store all subsequences. And for short windows, we can assume we are able to store all the results. What we also know is that the level bound can be computed in nwk squared. Now, if we luckily have pre-compute all needed subsequences for examination of a new sequence that can be retrieved in amortized complexity O1, the level bound can be computed in nw. This is the theoretical speedup. Of course, the real benefit depends on how sequences are generated and how efficiently we can reuse the stored solutions. The proposed fast sequence rejection is employed in the VNS-based solution of the DTSP, where two sequences sigma prime and sigma double prime are generated by shake and local search procedures. The initial incumbent solution is found by the cheapest insertion. Then, for a given computational time, we shake the incumbent solution and perform the local search for n squared times. So we have sigma prime and sigma double prime that are probably very similar, and we can reuse the results of the subsequences. We call the reject function and examine if sigma double prime is a better candidate sequence than the sigma prime with respect to the current best solution. We start with the window of the size 1 and check if the lower bound is below the cost of the current best solution. If so, we consider a larger window to get a better lower bound estimate. If not, or we reach the maximal window size, we compare the lower bounds to reject or accept the sequence sigma double prime. We compare the lower bounds with the true cost to save the computational time, because once the lower bound is above the true cost, it is likely a better sequence and we do not need to use longer windows. After n square calls of the local search, we need to decide if the current candidate sigma prime is better than the current best solution. We can use the true cost, or we can use the rejection schema to estimate the sequence quality, which is utilized in the reported results. The important part of the fast rejection is that for any of these lower bound estimates, we check the hash map for reuse or store the new results. Let's take a look how the proposed fast sequence rejection is performing. We consider a VNS-based solution of the DTSP and take 100,000 sequences and examine the computational cost. The details on the computational environments can be found in the paper, and here we focus on the results. The baseline approach is usage of the true cost for the discretization schema HK. In average, the examination of the sequence takes about 6.5 milliseconds, and all sequences are examined in about 11 minutes. For the proposed fast sequence rejection, we examine two variants, without storing the results and with the hash map for results reuse. What we can see is that for window size 1, we need to examine all sequences, which is not surprising. But it is quite interesting that most of the rejections are actually performed using the window size 1, even though the very large windows 32 is more demanding than the true cost. The overall benefits is in rejecting most of the sequences using short windows. If we introduce the reuse of the results, we significantly improve the computational performance, because for many subsequences, results are successfully retrieved from the previously stored solutions. The benefit of the proposed fast sequence rejection in the VNS-based solver has been further studied for DTSP instances and compared with two state-of-the-art approaches. The first is the transformational method, where the generalized asymmetric traveling salesman problem is transformed to the asymmetric TSP using Dubins transformation and solved by a heuristic solver LKH. The other method is an evolutionary-based approach that is currently the best performing DTSP solver we are aware of. It has been introduced in 2020. It utilizes learned surrogate model for quick sequence cost estimation. The surrogate model is learned using very similar windowing technique that allows scaling for arbitrarily long DTP instances. So it is learned for a relatively small sequence but with very dense heading samples. We use 1024 samples for training the surrogate model, and it takes hours or even days to train it. If we take a look at what the solution cost is according to the computational time, the evolutionary method with the surrogate model is very quick and provides high-quality solutions. It doesn't need a significant initialization, as the model is pre-learned. It is not the case of the VNS-based and transformational methods, where Dubins paths are pre-compute for all possible connections between the locations. An instance initialization is needed for asymmetric TSP. What is quite surprising that even for relatively sparse 64 heading samples per location, in comparison to the surrogate model, the VNS-based solver outperforms the evolutionary method. We are able to provide the best solutions. It is also visible that using the transformational method doesn't really make sense, because it is more demanding and doesn't provide good solutions. It might be possible that optimal solution of the generalized asymmetric TSP would provide better results. However, it would be very computationally demanding. Let me conclude the presentation of the proposed fast sequence rejection. The address Dubins Traveling Salesman Problem is solved as a sequence generation with assessment of the sequence quality using a solution of the Dubins Turing problem. The proposed idea of quick sequence assessment is based on estimation of the Dubins true cost using lower bound. The employed windowing schema enables efficient reuse of the partial results for subsequences that significantly improve scalability of the VNS-based solver to the DTSP. The performance of the presented solver might be further improved. However, the key principle of splitting the computation using the windowing schema already demonstrated its computational benefits. Thank you for your attention.